In this lecture, Mr. Sibang, we have started with this concept of the flow of current and basically the difference between the flow of current and the flow of electrons. Any doubt? We understood that the conventional flow of current, if the conventional flow of current is this side, then the flow of electrons is towards this side. Any doubt? So this would be the conventional current. Conventional current. This would be the flow of electrons. And there are historical reasons for that. We understood that. We understood the difference between high potential and low potential. Any doubt earlier? So this is where we discussed the difference between the lower potential and the higher potential. Okay. Then we understood the concept of resistance, and we also understood that what is the resistance of the joining wires. Okay. Then we understood the difference between insulators and conductors. Any doubt earlier? We understood the we understood the importance of metallic bonds. We understood why insulators and conductors differ. We understood why diamond is an insulator and why graphite is a conductor. Then we also understood that the charge can only exist in multiples of 1.6 into 10 to the power minus 19 coulomb. Using this, we were able to derive the formula that current is equal to charge upon time, and charge can be written as n, that is the number of the integer number into the charge carried by one electron. We derived at this formula. Then we understood the difference of potential and potential difference. We understood that work is needed to be done on a charge to move it from lower potential to higher potential. The formulas that we were able to understand was I is equal to Q by T, I is equal to NQ by T, VB minus VA, work done in moving charge from A to B per unit charge. Mr. Sibang, any doubt?
No doubt.
Great, sir. Mr. Satya, electricity class 10th. Okay, so let's start. So Mr. Satya, the first thing is that what we need to understand is that the convention is, this is how the circuits usually look like. So for example, this is a cell. This can be thought of as a bulb. Now this bulb is a form of resistance. Mr. Satya, any doubt?
No, sir.
There would be a key in the circuit. This is called the key.
So bulb also has a sign, right?
Yeah, bulb has a sign, but this bulb, see, basically what I'm trying to tell you is that any equipment in your house, any electrical equipment in your house is basically a resistance. Any doubt?
No doubt, sir.
So usually when you will see circuits, the circuits will be drawn something like this. So this, instead of the electrical equipment, you will see a resistance in the circuits. Any doubt?
No, sir.
So this is a cell. If you have two or more cells, this is called a battery. This is the positive charge, this is the negative charge. Any doubt till here?
No, sir.
So this longer stick is the positive, the shorter stick is the negative. Any doubt till here?
No doubt, sir.
So we are starting from absolute basics. Now what we need to understand is there is a, you'll have a confusion whenever you are studying electricity. Now the current flows like this. The current flows from positive to the negative. From positive to the negative. Have you understood?
Yes, sir.
Now this is the flow of current. Now what you need to understand is, now due to historical reasons, see, current electricity was being studied even before the electron was discovered. Have you understood?
Yes, sir.
Mr. Shivang, any doubt?
No doubt.
So what you need to understand is that, I won't go into details. So for example, Mr. Benjamin Franklin, now he was studying electricity years before electron was discovered. Mr. Satya, have you understood what I said?
Yes, sir.
So historically what they said was that the current flows from the higher potential, which is the positive charge, to the low potential, which is the negative charge. So historically, before the discovery of electron, they were saying that current flows from the higher potential, so the positive terminal was the higher potential and the negative terminal was the lower potential. So they said ki, like water flows from higher potential. So for example, if this is a roughly, if this is a mountain, this is a mountain, so the river will flow from top to bottom. Any doubt?
No, sir.
So this is the higher potential and this is the lower potential. Mr. Sivang, any doubt?
No doubt, sir.
So what you need to understand is that things like water. So for example, this is water. Water will flow from higher potential to lower potential, lower potential. Similarly, you will also you will always find that things will fall down a table. Have you understood what I've said? Mr.
Yes,
Sir?
sir.
So if this is a table and this is a glass which is there on the table, the glass will fall down. It won't rise up. Any doubt?
No doubt.
No, sir.
So why does the glass fall down? Because this is a higher potential, this is a higher potential, and this is a lower potential. So similarly, they said that the charge will flow from the higher potential, which is the positive, to the lower potential. This is how the books were written before the discovery of electron. Mr. Satya, any doubt?
No, sir.
But then once electron was discovered, what they understood was that actually it is the flow of electrons which causes the flow of current. Any doubt?
No, sir.
Satya, is it getting confusing?
No, sir.
Now the flow of electrons is like this. Any doubt?
No, sir.
So now we are in a situation where the conventional current, what is the conventional current? The historically which has been decided. The current flows from positive end of the battery or cell, from positive end to the negative end, but we understand that the flow of electrons is opposite to this conventional current. Mr. Satya, if you are having any doubt, please stop.
Oh.
Mr. Sibang, any doubt?
No doubt.
Mr. Satya, should I go ahead?
Yes, sir.
So, whenever you draw a circuit, I am starting from absolute basics. Whenever you are drawing a circuit, just remember 2-3 things. One, this resistance can be any electrical equipment. So basically what I'm trying to tell you is that the fan in your house, the tube light in your house, the bulb in your house, all of them are examples of, Mr. Satya, resistances. Any doubt?
No doubt.
This is a symbol of a key. And what you need to understand is there is another very important thing that you need to understand whenever you are studying electricity is that this resistance of the joining wires is negligible with respect to the main resistance. Mr. Satya, have you understood what I've said?
No, sir.
No, sir. Yes, sir. Mr. Sibang, have you understood what I've said?
Partly, sir.
Okay. So Mr. Satya, what I'm trying to tell you is that if we say that this is a, let us assume that this is a circuit that we are discussing. Now, if the resistance of this is 10 ohm, then every electrical equipment would have a resistance. Do we agree to this or not?
Yes, sir.
Now, if everything has a resistance, of course, this electrical wire should also have a resistance.
Yes, sir.
Mr. Satya, do we agree?
Yes, sir.
And of course, this cell would also have some internal resistance. Have you understood, Satya?
Yes, sir.
But usually when we are discussing the electrical circuits, what we assume is that the resistance in the joining wire is negligible. So the resistance of the joining wire can be 0.0001 ohm. Have you understood what I've said, Satya?
Yes, sir.
Any doubt, Mr. Shivang? Any doubt?
No doubt.
So please understand, when we are discussing the electrical circuit, because once you start doing the electrical circuits, one day or the other you will have this doubt that what about the resistance in this wire? Maybe in this class or the next class, or sometimes you'll have a doubt. But the point is that yes, of course, this wire has a resistance, but the resistance of the joining wires, the wires which are connecting the circuits, is negligible in front of this main resistance. Is it making sense, Mr. Satya?
Yes, sir.
Mr. Satya, is it
Yes.
making sense? And another thing that you need to understand is that any electrical equipment or wire will always have a resistance. Do we agree to this?
Yes.
Mr. Sipang?
Yes, sir.
So let us review what we have discussed till now. The most important thing that we have understood till now is that if this is the flow of conventional current, the conventional current will flow from positive end of the cell or battery to the negative end, and the flow of electrons, Mr. Sibang, will flow from
Negative to positive.
negative to positive. Mr. Satya, are we clear?
Yes, sir.
So let us call this electron current. Mr. Satya, any doubt till here?
No doubt, sir.
Please understand that there is something called, okay, let me take a simple example. See, whenever we discuss of a current carrying, have you seen a wire, Mr. Satya?
Yes, sir.
Do you know what the wire is made up of? Have you seen?
Copper, I guess.
Copper. Shabash. So usually if you see this any household wiring, if you have seen an electrician working, you would see there would be this you would see that there is this plastic covering, and inside the plastic covering there is this copper wire. Satya, have you seen?
Yes, sir.
Mr. Sibang, have you seen?
Yes, sir.
So in our household, we'll see a wire like this. There would be a this insulating covering, and inside that insulating covering there is a copper wire. So if you see a iron, basically if you see a iron, if you have ever ironed your clothes, you will see there is a insulation above that copper wire. Mr. Satya, are we comfortable till here?
Yes, sir.
Now what I want to tell you is that the difference between an insulator and a conductor, because this is a common example, so it will be easier to understand. So for example, this insulator, of course, an insulator and a conductor, both of them have electrons in them. Do we agree to this?
Yes, sir.
Yes, sir.
Both of them have electrons. But the only difference between an insulator and a conductor is that for a conductor, so for example, if I look at this copper wire, basically, Satya, what happens is that what we say is that there are these atoms with the nuclei, and you have these sea of free electrons. Mr. Satya, am I making sense, or am I confusing the things?
No, sir, making sense.
Mr. CB, am I making sense?
Yes.
So what we say is there is a sea of electrons in conductors, which are free to conduct electricity. Mr. Satya, am I making sense?
Yes, sir.
Of course, see, Satya, what I'm trying to tell you is that, of course, in an insulator also, in a plastic or a glass or an insulator, of course, there is a positive nucleus, there are electrons. But Mr. Sibang, what is the difference? Mr. Sibang, what do you think is the difference?
So the
Yeah, Shabash. In an insulator, Satya, can you guess what will be the difference between insulator and a conductor?
so sea of electrons would be less than.
Okay, Mr. Satya, can you guess? Mr. Satya, can you guess?
Also, in an insulator, like both the charges are together, I guess. Like there are same amount.
See, okay, 50% of your answer is correct. See, what happens is, in an insulator, this electron which is there with the proton is not free to conduct electricity. But have you understood?
Yes, sir.
Mr. Sibang, have you understood?
Yes, sir.
Okay, let us take a simple example. Let us take a very simple example. That we have two houses. Mr. Satya stays in this house. Mr. Satya. Mr. CB stays in this house. Mr. CB. Okay. Now, Mr. Satya is free to move out of his house. Of course, he goes to the market, he roams around, and then he comes back. Satya, have you understood?
Yes, sir.
But Mr. CB is not free to go out. He has to remain inside the house because his parents are very afraid of COVID. Mr. Satya, have you understood?
Yes, sir.
So Mr. CB just keeps roaming inside the house. Mr. Satya, have you understood the difference?
Yes, sir.
See, please try to understand that there are protons, there is a positive nucleus, and there are electrons in a conductor. Of course, there is a positive nucleus and there are electrons in a insulator. Because what we have studied in our basic atomic structure is that there is a positive nucleus and then there are electrons which are around the positive nucleus. Mr. Satya, do we agree?
Yes, sir.
See, the basic structure of an atom remains the same. There is no difference at an atomic level between a conductor and an insulator. But what is the difference, Mr. Sivang? Have you understood now?
So the difference is that in a conductor, even if you have pairs, there are more electrons free. So there are free electrons to conduct electricity. But in insulator, you do not have free electrons.
You do not have the electrons or the freedom?
No, the freedom is not there.
Freedom is not there. Mr. Satya, any doubt?
No doubt, sir.
So this is what is happening in a copper wire. So in a copper wire, what happens is, so basically I'm just starting with the absolute basics of electricity. So in a copper wire, the copper wire is this is a rough model how a copper wire looks like. Mr. Satya, can you see?
Yes, sir.
So Mr. Satya, these are free electrons. These are free electrons. So in a copper, the free electrons are allowed to go this side, this side, this side, this side, this side, this side. Because they are free, that is why they, whenever required, they would be able to conduct electricity. Is it making sense, Mr. Satya?
Yes, sir.
तो अब ये जो Mr. Satya is free. So अगर if you want bread from the market, or you want eggs from the market, or you want milk from the market, Mr. Satya can go out and he can bring the milks or the bread or whatever you require, because he is free to move. But in an insulator, it has electrons, but it is not free to move. So the only difference between this insulator wire and this copper wire, both have positive nucleus and electrons, but the only difference is that in an insulator, the electrons are not free to move about, but in a conductor, the electrons are free to conduct electricity whenever required. So Satya, are we clear?
Yes, sir.
Now in chemistry, using this model, just remember that in chemistry, using this model, you will study something called a metallic bond. Now when you study metallic bond, this same sea of electrons and this positive nucleus concept would be repeated. Mr. Satya, have you understood?
Yes, sir.
Do you remember the bonds that we had done? Covalent bond, ionic bond,
Yes.
and this is the third kind of bond, which is called the metallic bond. Mr. Satya, any doubt till here?
No doubt.
Now, Mr. Sibang, I think he will be able to tell us. Mr. Sibang, out of diamond and graphite, which is an insulator and which is a conductor?
So diamond will be an insulator, but graphite will be a conductor.
Why, Mr. Sibang?
So because in diamond you don't have the electrons don't have freedom to move, but in graphite they do have freedom to move.
No free electrons. Mr. Satya, is it making sense?
Yes, sir.
So again, when we are doing chemistry, we'll be discussing this in detail. And there also we will discuss this part only, that what is the difference between the behavior of diamond and graphite. So remember that diamond is an insulator, but graphite is a conductor. And Mr. Sibang, what is the funny part about these two, diamond and graphite? What is the
So both of them have carbon bonds.
Shabash. Both of them are allotropes of carbon. Shabash. Mr. Satya will discuss this in detail in chemistry. But have you understood what I have discussed till now?
Yes, sir.
So till now we have understood the basics of electrical circuit. We have understood what is the difference between a conductor and an insulator. We have understood what is a metallic bond. Typically, I actually just wanted to show you a typical circuit. So, Mr. Satya, this is how a typical circuit will look like. One second. Yeah. So this is how a typical circuit will look like. Can you see, Mr. Satya?
Yes, sir.
So this is the positive charge, this is a negative charge, this is the resistance, and if you see the flow of current, is always from the positive end of the terminal to the negative end. But is it clear or not?
It's clear.
And always remember that this resistance can be any electrical circuit. Remember that the resistance of the wire is negligible compared to this resistance. Is it clear, Mr. Sibang?
Yes, sir.
And of course, we'll study the internal resistance of a cell also. So if you understand, the cell also has some internal resistance, which is a separate topic. I think we'll discuss this in the next lecture. So, any doubt till here?
No doubt, sir.
Okay. So once we are finished with this basic thing, let us do few formulas. See, one thing that you need to understand is that the charge is measured in coulomb, and current, Mr. Sibang, is measured in
Ampere.
Mr. Satya, any doubt?
No, sir.
Okay. Now, the definition of current is that if I have a conductor like this, let us assume that this is a copper wire, and this is a cross section. Satya, have you understood?
Yes, sir.
Now, if you imagine this just imagine a plane, and just, Mr. Sibang, am I audible?
Yes, sir.
So Mr. Satya, to define current, what we assume is that there is this, just assume a surface. And if you are able to, see, this is the definition of current. If you are able to measure how many electrons are drifting to this side per unit time, that is, number of electrons drifting per unit time, this would be the current. Mr. Satya, any doubt?
No doubt, sir.
Mr. CB, any doubt?
No doubt.
Let's try to understand this again. So I have this copper wire, and I have this. I have assumed a surface. And let us assume that I'm sitting here or I'm standing here, and I can measure. I can measure the number of electrons which are drifting in the left side. The current. Just remember that the conventional current is always opposite to the flow of electrons. Mr. CB, any doubt here?
No doubt.
So the definition of current would be charge per unit time. Mr. Satya, any doubt?
No doubt, sir.
Current is measured in ampere, charge is measured in coulomb, time is measured in second. So ampere is equal to coulomb per second. Mr. Satya, any doubt?
No, sir.
Okay. Now here we need to understand something, that the current is carried by electron. Now the charge can only exist in multiples of charge carried by one electron. Mr. Satya, is it confusing?
Yes, I understand that.
Yeah. So let us try to understand that one electron has a charge of 1.6 into 10 to the power minus 19 coulomb. Is it okay till here?
Yes, sir.
Okay. So the charge can only exist in integer multiples of this. Any doubt?
No doubt.
Mr. Satya, there is a doubt still. So what I'm trying to tell Mr. Satya is that if you have 1.6 into 10 to the power minus 19 coulomb, now you can multiply this by 1, you can multiply this by 2, you can multiply this by 100, you can multiply this by 10,000, you can multiply this with 1 million, you can multiply this with 10 billion. But you can't multiply this by 1.5. Mr. Satya, is it making sense?
Yes.
So see, it is like, okay, let us take a very simple example. If you go to a market, if you go to this vegetable vendor, do you think he will give you 2.5 bananas? Mr.
No,
Satya?
sir.
Why? Mr.
Like
Satya?
half, I don't know. Half, the
He
half
won't give
can be
you,
sold.
yeah, he won't give you half. He will always give you 2 bananas, 3 bananas. He will give you 24 bananas. He will give you 36 bananas. But he won't give you 2 3 by 4 bananas. Is it making sense now?
Yes, sir.
Again, the same vegetable vendor. Do you think he will give you 3 1 by 4 oranges? Mr. Satya?
No, sir.
So what I'm trying to tell you is that oranges and bananas and apples, they only exist in integer multiples. You can only have 10 bananas. You can only have 15 bananas. That is for buying and selling. People don't buy and sell 15.75 bananas. Is it making sense?
Yes.
Yes, sir.
Similarly, Mr. Satya, what I'm trying to tell you is that the charge carried, because the charge is always carried by electrons, and one electron can carry a charge of 1.6 into 10 to the power minus 19 coulomb. So you can have charge only in multiples, integer multiple or integral multiples of this quantity. Mr. Satya, is it making sense now?
Yes, sir.
Mr. Sivang. So what I'm trying to tell you is that you won't have a charge like 0.8 into 10 to the power minus 19 coulomb. You can't have this because this implies charge carried by half electron. Is it making sense now?
Yes, sir.
Mr. Satya. Have you understood the meaning of integral multiples?
Yes, sir.
Satya, is it making sense or should I take more examples?
No, sir. Yes, it's okay. I understood.
Okay. Now let us understand. Now there is an important question lying here. Now let us try to understand what does this means. So basically what he is saying is that if you have one electron, let us say you have one electron can carry a charge of 1.6 into 10 to the power minus 19 coulomb. Satya, is it making sense?
Yes.
Now if I need 1 coulomb charge, then the natural question is, how many electrons do I require? Satya, is it making sense?
Yes.
Mr. Sibang. So Mr. Sibang, for 1 coulomb charge, how many electrons will be required?
So 1.6 into 10 raised to the power 19 electrons.
Mr. Satya.
Yes, sir.
Okay, let us take a simple example. I think let us take an example like this. So for example, if one electron had a charge of 1 by 4 coulomb and I need 1 coulomb, so how many electrons do I require, Mr. Siba?
4.
4. Is it making sense, Satya?
Yes.
Let us assume that 1 electron is equal to 1 by 100 coulomb, and if I require 1 coulomb, then how many electrons I require, Mr. Siba?
100.
100 electrons. Mr. Satya, is it making sense?
Yes.
But now the issue is that 1 electron is equal to 1.6 into 10 raised to the power minus 19 coulomb. To make the things easier, let me write it like this. 1 electron is equal to 16 upon 10 into 1 upon 10 raised to the power 19 coulomb. Sivang, is it making sense?
Yes.
Further, let me write this as, now 10 upon 16, let me calculate 10 upon 16 for you. 10 divided by 16. This is 0.625 coulomb. Mr. Sibang, is it making sense?
Yes.
So Mr. Sibang, if 1 electron, now just try to see the logic and now maybe you will be able to understand. If 1 electron was equal to 1 by 4 coulomb, then 1 coulomb was equal to, Mr. Sibang?
So 1 coulomb would be equal to 4 electrons.
4 electrons. Now if I ask you that 1 electron is equal to 1 upon 0.625 into 10 to the power 19 coulomb, Mr. Sibang, then 1 coulomb would be equal to
0.625 into 10 raised to the power minus 19 electrons.
So that is making some sense.
Yeah.
And therefore 1 coulomb can be written as 6.25 into 10 raised to the power 18 electrons. Mr. Sivang, any doubt still?
No doubt, sir.
Mr. Satya?
No.
Mr. Satya, Mr. Sivang, this will be an important question for you, and that is why you need to understand this can come as a MCQ also in the exam. Basically, this is what I'm trying to tell you, that 1 coulomb charge means a deficit of 0.625 into 10 raised to the power 18 electrons. Sivang, have you understood this?
Yes. Yes.
Satya, have you understood 50% of what I've said?
Yeah.
Basically, the important thing that you need to understand is that the charge will always exist as some integer into 1.6 into 10 raised to the power 19 coulomb, and this n would always be an integer. Mr. Sibang, any doubt?
No doubt.
So basically, my current is charge upon time. My charge is always n into charge of 1 electron into 10 raised to the power minus 19 coulomb by time, and therefore the formula that you will see is current is equal to n into charge carried by 1 electron upon time. Mr. Sivang, any doubt?
No doubt.
Mr. Satya, this would be a bit tricky to understand, but I hope you have understood. Mr. Satya? Mr. CB?
Yes, sir.
Any doubt?
No doubt.
So basically, this is the formula that we have to write. Mr. CB, have you understood?
Yes, sir.
And this is the definition we started with. I is equal to Q by T. Mr. CB.
Yes, sir.
Now, Mr. CB, what you need to understand is before we go forward, see the formula that we have derived till now, I is equal to Ne upon T. Now, if you see questions like these, Mr. CB, can you see question number 1 and question number 2?
Yes.
In a conductor, 6.25 10 raised to 16 electron flow from 1 end to 2 second. Find the current flowing. So, CB, would you be able to do this question?
Yes, sir.
Second question, current of 1.6 milliampere flows if charge of this, find the number of electrons that pass per second cross section of the area. So these are the two questions that you will be able to do now, Mr. Sivan.
Yes, sir.
Okay. Now another thing that we need to understand before we go forward is that we should be very comfortable with this conversion, metric conversion, Mr. CB.
Yes, sir.
And Mr. Satya, you need to cram this. That deci is 10 raised to the power minus 1, centi is 10 raised to the power minus 2, milli is 10 raised to the power minus 3, this is micro, this is nano, and this is pico. Mr. Satya. Mr. Satya.
Yes. Yeah.
We should cram this conversion. Kilo means 10 raised to the power 3, mega means 10 raised to the power 6, giga means 10 raised to the power 9. These are important conversions, Mr. CB.
Yes, sir.
Giga, mega, kilo, deci, centi, milli, micro, nano, pico. These are the conversions that are usually used. And if you don't know the conversion factor, you will get confused. Satya, any doubt here? So this is what is being discussed here. The same thing. Milli will mean 10 raised to minus 3. Micro will mean 10 raised to minus 6. Nano will mean 10 raised to minus 9. So you should be clear about this, because in questions they might ask you the conversion factor. Similarly, again, they have used the conversion factor here also. So if you see milliampere, if you see microampere, they are using 10 raised to minus 3 and 10 raised to minus 6. Mr. Sibang, any doubt?
No doubt.
Okay, then there are 2-3 things that Mr. Satya, you won't be able to understand now. Mr. Sibang, you will be. One thing is that current is a scalar quantity. Mr. Sibang.
Yes.
Another question. See, these are the MCQs, Mr. Sibang, which will be asked. So this is one of the MCQ which will be asked. Another MCQ that they can ask is that current is measured in ampere by using an ammeter, and the ammeter is always joined in series in a circuit. Mr. Sibang, any doubt?
No doubt.
So these are the typical MCQs that they'll ask. Mr. Sibang, any doubt till here?
No doubt.
Okay. So once we are comfortable with this, then let us try to understand what is the meaning of potential, and then we'll understand what is the meaning of potential difference. Mr. Sibang. So Mr. Satya, let us assume that this is a positive charge, any positive charge. Let us assume, just to take a number, let us assume to make the things easier, this is plus 1 coulomb of positive charge, and I'm trying to bring, let us assume, another plus 1 coulomb charge. This is my sphere A, this is my sphere B. Mr. Satya, do you think you would be able to bring this B charge very comfortably towards A charge, Mr. Satya?
Yeah, I guess.
Mr. Siva?
Yes, sir.
Sir, I'll repeat my question. This A is plus unit 1 coulomb charge, and this B is plus 1 unit 1 coulomb charge. Mr. Sivang, do you think comfortably you will be able to bring this very, very close to this?
No, sir.
Why, Mr. Sivang?
Because they are like charges.
So, like charges?
Well,
Mr. Satya, have you understood what he has said?
Yes, sir.
Can you repeat what he has said?
So he said they both can come together because they are like charges. So like the same.
Shabash. But now let us assume that this is the plus 1 coulomb charge, this is the plus 1 coulomb charge, plus 1 coulomb charge, and this is plus 1 coulomb charge. You still want to bring it here like this. What you will have to do, Mr. Siva?
so you have to give energy.
You have to give energy, or you have to do some work. Satya, is it making sense?
Yes.
Right, Satya, it's the same thing like we started in the during the lecture. This is the example that we started with. So let us assume that this is a book which is lying on the table, on the ground. A book on the ground. Satya, do you think automatically this book can go to and sit on this table, Mr. Satya?
No, sir.
Why, sir?
So because someone has to pick it up. It is the low one. So
But
it
why
can
somebody?
go too high.
Okay. What I'm trying to ask is why somebody has to pick it up, Mr. Siva?
So because it requires work.
Why does it require work? See,
So
fundamentally.
because if you have to take it to lower to higher potential, it requires work.
Satya, is it making sense?
Yes.
Satya, what has Shivang told now?
So that if you want to take something from lower potential to higher potentials, it needs work.
You have to do work, na? So another simple example that we can take is that I am teaching now. I am teaching you guys now. So what I can assume is that I am at a higher potential. Mr. Satya, do you agree?
Yes, sir.
So I am at a higher potential and I am trying to bring you guys to the higher potential. Is it making sense, Satya?
Yeah.
Mr. Sibang, is it making sense?
Yes, sir.
So we can assume something like this, that I am at a higher potential. You two guys are currently at a lower potential. I am trying to bring you guys to the higher potential. That is why I am doing work. Satya, is it making sense?
Yes, sir.
This is lower potential, this is higher potential. Okay. Now let us assume that in the next 3 years, you guys reach this position, Satya. Now you are at the same potential as I am. Satya, is it making sense?
Yes, sir.
Now Mr. Satya goes to London, gets educated, gets a PhD in physics, is working in CERN now, or let us assume he is working in NASA. Now Mr. Satya is at a higher potential. Mr. Satya, do you agree?
Yes, sir.
And I ask Mr. Satya, please help me come to this level. So Mr. Satya will have to do a work now because Mr. Satya is at a higher potential. Mr. CB, is it making sense? Mr. Satya? Mr. Satya, is it making sense?
Yes, sir.
So from lower potential to higher potential, if you have to raise something, Mr. Satya, what do you need to do?
Work.
Work. Do work. Are we clear till here or not?
Clear, sir.
Now let me simplify these things. We'll take the same example to understand the same thing. This funda of potential is the same for electricity as well as for gravitation. We are not doing gravitation now, don't worry. But what I'm trying to tell you is that the funda are the same. So this is me, this is Mr. Satya. Let us assume that this is Mr. Satya on 2022. So this is me at 2022. But this is Mr. Satya. This is Mr. Satya at 2030. Satya, is it making sense?
Yes.
So Mr. Satya at 2022 is at a lower level. I am at a higher level. I have to bring Mr. Satya to this level. So I'll have to do work on Mr. Satya. And at 2030, if Mr. Satya has to bring me from lower, because then I'll be at a low potential, he'll be at a higher potential, then he'll have to do work on me to bring me at a higher level. Mr. Sibang, Mr. Satya, are we clear?
Yes.
Yeah.
So Mr. CB, have you understood the concept of lower potential, higher potential,
Yes, sir.
and work to be done? Any doubt?
Alright.
So what I've told you now is that whenever you are studying gravitation and whenever you are studying electricity, you will find this concept of potential and work. In both of these cases, these concepts are used. Mr. CB, any doubt till here?
Alright.
Okay. So now in this example, this is the lower potential. Do we agree?
Yes, sir.
This is the high potential. Do we agree?
Yes.
And someone has to do work. So for example, if this is a person, this person is an external person, let me call this external entity who will be doing work. Do we agree?
Yes.
1 second. So Mr. Sibang, what we are discussing now is there three words we are discussing. One is a lower potential, other is a higher potential, and the third is work. The work is done by the external entity. The book is at a lower potential. I need to raise it to the higher potential. So I'll have to do some work on this book to take it from low potential to high potential. Mr. Sibang, are we clear?
Yes.
Now, Mr. Sibang, what we need to understand is in electricity also the same concept is used. So you would have an electron which will be at a lower potential. Now this electron from lower potential has to be raised to a higher potential. Is it making sense?
Yes.
Work would be required to be done on this charge to move it from lower potential to higher potential. And Mr. Sibang, can you tell me what will be doing work on this charge to move it from lower potential to higher potential?
Potential difference.
I'm sorry. See, the charge has to be moved from lower potential to higher potential in an electrical circuit. Who does work? Who does work in an electrical circuit? Can you identify, Mr. Sima?
So the battery.
The battery. Any doubt?
Alright.
So basically, the cell or the battery. What is the job of cell or a battery in a circuit, Mr. Sima?
So the job is to get the charges from a lower potential to a high potential.
Shabash. Very nice. So job of cell or a battery is to move the charges from lower potential to a higher potential. So Mr. Sivang, if this cell is not able to move the charge from higher potential to lower potential, what will we say about this cell? If it is not able to do its job, what will we say?
So that the battery is spoiled or the circuit is damaged.
Shabash. The cell is dead. So for example, in your remote, if the remote is not working, what do?
So we change the cells.
You change the cell. And how? The new cell that you put in this remote, what does it do? Now it is in a position to do work on the charges. Any doubt?
No doubt.
So basically, this is how you can imagine. This is how you can imagine a circuit to be. You can imagine that these are the electrons. These are the electrons. And what is the job of a battery, Mr. Sivan?
Job of a battery is to get the charges from low potential to high potential.
Shabash. The job of a cell or a battery is to move the charges from low potential to high potential. High potential. Is it making sense now?
Yes.
So, Mr. Sivang, have you understood the concept of a potential?
Yes.
And what you need to understand is that potential at a point is defined as work done per unit charge. Any doubt?
No doubt.
Now, just to detail this definition, basically what we assume, Mr. Sivang, is that this low potential, this zero potential, is assumed to be at infinity. Any doubt?
No doubt.
Mr. Sivang, let us try to understand this closely. So what this means is that this charge B, that we want to bring it close to here, this charge is at infinity. Any doubt?
No doubt.
So this level, when we are studying gravitation, this level is assumed to be zero potential in gravitation. Now this is what we assume when we are in class 10th. Of course, the definition will change when we go to class 11, but more or less the concept is the same. So this is assumed to be the zero level, and you want to reach till here using the definition of mgh. The work that you need to do to raise this book of mass m to height h, this would be the work which will be required to be done. Mr. Sivang, any doubt?
No doubt.
Now similarly, if this is my charge, this is my, let us assume, positive charge, and I want to bring a test charge. This is called a test charge. A test charge is as small charge as possible. So basically, the work that I need to do to carry this test charge close to this body is called as the potential at a point. So if this is a point, if this point is x, then the potential at point x will be the work done per unit. Let me call this test charge. Mr. Sivang, any doubt?
No doubt.
So, Mr. Sivang, the discussion that we had now regarding the potential, this is the potential. There was a potential at a point in a region of charge is measured in terms of work done in moving a test charge from a point of zero potential to that point. So that is what I was explaining here, that this test charge is assumed to be at infinity. At infinity, the potential is zero. So you are basically, in terms of gravitation, you are moving the charge from a lower potential to a higher potential. Any doubt?
No doubt.
This is similar like raising a book of mass m from this lower potential, which we have assumed to be zero potential, to be kept on this table, which is the higher potential. Mr. Sivang, any doubt?
No doubt.
Now let us try to understand. So one definition that we need to understand is that potential at a point is equal to work done per unit per unit test charge. Now potential, the concept of potential is the same as we have discussed for gravitation, that if there is a book lying on the table, this is a book lying on the table, and I assume this to be zero potential, I raise the book from here to here, I increase the potential of the book, therefore I have to do work on the book. In case of gravitation, the work is done by a person, and in case of electrical circuit, the work is done by the Mr. Sivang.
The work is done
By the battery. Any doubt here?
No doubt.
Okay. Now, another thing that we need to understand is that, let us assume I have raised the book to, I've raised the book, this point is point A. Now there is another table. Let us assume that there is another table here. There is another table here. Now let me call this point as point B. Mr. Sibang, is it making sense?
Yes.
Now the potential at point A, let me call that VA, and potential at point B, let me call it VB. Now the book has to be raised from point A to point B. Mr. Sibang, is it making sense?
Yes.
Now this VB can be also defined as the work that is required to be done to raise this book from 0 level to here. Mr. Sibang, is it making sense, or I'm
Yes.
confusing the issue?
No.
So there is something called VB minus VA, and that is called the potential difference. Mr. Sibang, any doubt?
No.
I'll try to explain this concept again. I hope it makes sense now. Let us assume that this is zero potential. Zero potential. When the book is kept here, kept here, let me call this potential 5 units. So the potential at A point is 5 units. With respect to ground, the potential at point B is 15 units. So can I say that the difference between VB minus VA is 15 minus 5 is equal to 10 units? So basically this 10 units would be the work which is required to move the book from point A to point B. Mr. Sibang?
Yes.
Any doubt?
No.
So VB minus VA is work done in moving charge from A to B per unit charge. Any doubt, Mr. Sibang?
No.
So you will find a definition like this: VB minus VA is work done in moving a charge from A to B divided by the charge moved. Any doubt, Mr. Sibang?
No.
And this is a definition which is, so these are the formulas which are mentioned here. Unit of potential, work done per unit charge. This is the first formula. The other formula that is discussed is VB minus VA, work done per unit charge. Mr. Sibang, any doubt?
No.
Okay, so we'll do this concept of resistance and Ohm's law after a break. Mr. Sibang, is it okay?
Okay.
Now before we finish this part, just let me tell you the units which are used here. So potential is measured in volt, work is measured in joule, Q is measured in coulomb. So always remember that joule is equal to volt into coulomb. Mr. Sibang, any doubt?
No.